Okay, I don't want to waste any time, so let's get started. So today we're going to be talking about logistic regression, all right? Logistic regression is a classification algorithm. So previously what Dr. Jasky has kind of introduced to you and what you've seen is like regression algorithms that are linear. And these problems are a little bit different, so we're going to be talking about problem setup, hypothesis, all of that. So this is the plan for today. Really, we're going to talk about the logistic regression problem. We're going to talk about the hypothesis function, which is the function that defines logistic regression. And then we're going to talk about gradient descent and loss. And I'll explain what all of these mean, but let's start with the problem setup. So really, we're talking about what type of problem can we use for logistic regression. So the best way to introduce any ML algorithm is with a problem. So I'm from New Jersey, I'm not from Arizona, and it gets pretty cold in New Jersey, so we have to wear these coats. I don't know if you Arizona people know what these are, but it can get up to like -10 degrees, so we have to, stay warm. So an example of a logistic regression problem is, let's say Tal was following me around for a year, and he was measuring the temperature, and he was recording whether I was wearing a coat or not, all right? And he made this little graph. He said, so the problem is classify based on temperature whether I will wear a coat or not. And so we see for the lower temperatures over here, I will wear a coat. And as the temperature increases, the frequency of me saying, yes, I will wear a coat decreases, and the frequency of me saying, no, I will not wear a coat in higher temperatures increases. This is like pretty intuitive, right? So as it gets warmer, I'm going to wear a coat less often. And so the idea here is that this is a classification problem. So we can attack this with some method that we already know. We can try to do a line of best fit. And now this hypothesis function, this line of best fit, it would look something like this. And then we would say that if h of x, m equals mx plus b, that's just the equation of some line, all right, with some slope m and some y-intercept b. If h of x is greater than or equal to 0.5, predict 1. And then this y-axis is just the probability of me wearing a coat or not. So if h of x is greater than or equal to 0.5, predict 1. Meaning, if this function is greater than or equal to 0.5, I'm going to say, yes, I'm wearing a coat. And then if h of x is less than 0.5, let's predict 0. I'm not going to wear a coat. And so we attribute these 1 and 0 labels based on this threshold 0.5. Now, this could kind of work. Like if you see, look at 0.5 here, we start to see that after 0.5, I'm generally like not wearing a coat. So in this case, like it would probably work because as we hit the threshold 0.5, we see that I'm basically no longer wearing a coat. But the problem comes when we add an outlier. And what happens to this line when we add an outlier? Well, we're fitting the line to the points, right? So the line actually changes. All right? And when the line changes, we look at this 0.5 threshold, we look at this 0.5 and then we see that now this threshold doesn't really work because we're ignoring some of these yes points and ignoring some of these no points. And so this line of best fit no longer allows us to predict whether I'm wearing a coat or not accurately because of this outlier. So this outlier kind of screws everything up. And so the idea is, can we create a function, or can we have some hypothesis function that can take this data and no matter what outlier we have, it can better, predict probabilities, because there's no temperature where I'm going to say, hey, okay, it's 70.9 degrees, I'm no longer wearing a coat. It's kind of a range, and it's not exactly linear. There's some kind of nonlinearity that exists here. So we've established that because of outliers either at the bottom or the top, this line of best fit does not work. Okay? And so our hypothesis has to predict the probability that y equals 1, that our label will equal 1, based on some input x. Okay? So going back to the previous slide, we need to predict whether y is equal to 1, so we have that probability, based on some input x. In this case, it's our temperature. Okay? So we know that if you guys have studied probabilities, the probability that y is equal to 0 based on some input x plus the probability that y is equal to 1 based on some input x is equal to 1. And we can refactor this equation to say that the probability that y is equal to 0 based on some input x is equal to 1 minus the probability of y equals 1 on some base input x. And so now here comes the fun part of logistic regression. We're discovering this new function that we can use to fit to that wearing a coat or not problem. And so our hypothesis function looks something like this. And this hypothesis function is called the sigmoid function. And it's defined as y equals, or our output function equals, 1 over 1 plus e to the negative z. All right, and z, you might see this and see the z and say, okay, this looks familiar. Well, this is just mx plus b. Why do we need to put a linear function within this sigmoid function? Well, if we go back to a couple of graphs ago, or a couple of slides ago, we'll see that this does not look the same. Like, this s might not look the same as this s. Do you guys notice what's different? Like, what's different about that previous problem versus this? So this s is flipped, right? It looks something like that. And the way we can adjust that is by playing around with these parameters, theta and theta 0, all right, or theta and theta naught. And we can play with those parameters until we find some sigmoid function that fits our data. So I want to show you guys some Desmos graph to better illustrate this function. So I'm going to exit here. And let me show you guys this. So if we click on Desmos, here I'll go to play from current slide. If we click on Desmos, it will just take me a second to share this with you guys. Okay. Let me just share this with the crowd back home. Here we go. Crowd back home, you'll be able to see that. Let me shrink that for you. Okay. This is what it looks like in action. It's going to be a little laggy. Let me make sure that you guys see this. Let's exit out of here. Okay. So you guys, can you see that graph? Perfect. All right, so this is our S, and this is our line. And we have these sliders. All right, so we said z equals theta x plus theta naught. It can also be formulated as wx plus b. It doesn't matter what you're putting in front of it. It's the general equation. And we're playing with w and b, and you can see that the S-curve is being adjusted in two ways. The slope is being adjusted, and it's being moved across the x-axis, okay? And so b is responsible for moving it, and then w is responsible for the slope. And you can see that illustrated in this little cool animation. Why am I showing you this? Well, if we have some data, I'm going to stop this, it's making me dizzy. If we have, wait, that's not a good place to stop. Okay. If we have some data, and let's say the 0 labels exist here and the 1 labels exist on the top, this S kind of sigmoid function will not suffice. We're going to have to adjust it and fit it to our data. So really the goal of our problem is to take W and B, play around with them until it fits to our problem, and we can create some S-curve, some sigmoid function that fits our data and can accurately predict or classify based on our input X. Okay. So now let's go back to the PowerPoint. Hopefully you guys can see that. Okay. Let me just make sure people at home can see it. Okay. So far, does anyone have any questions? I would love to answer your questions at this point. Any questions? Let's see in the YouTube chat if we have any questions. Feel free. There might be a little bit of a delay. Okay. So if there are no questions so far, so we need to fit the sigmoid function to some input data. And now the question is, how do we fit theta and theta naught, or W and B, weight bias, to our data? How do we fit these parameters? And in comes the cost function, or the loss function. Cost, loss, they're kind of interchangeable. And so this takes a little bit of explaining. So let me tilt this, okay. So the cost function defines the error between the predicted probability and our label, okay? We established initially that if our predicted probability was above that 0.5 threshold, then we're going to assign the label to 1, and if it's below that 0.5 threshold, we're going to assign the label to 0, okay? Now, the cost function tells us the error across all data points, and we're trying to minimize this cost function, all right? So let me tilt the screen so everyone at home can see the whiteboard. Hopefully you guys can see that. So let's look at a parameter, theta, we'll call it theta, all right? And then we have our cost here. We want to have a cost, we want to plot our cost based on the value of theta, okay? So imagine we have this convex function that represents the cost corresponding to theta, okay? Let's say our theta value starts at this point. We're trying to minimize cost so it reaches this global minimum. Okay? The idea is we'll be able to look at every value of theta and look at every value of the cost plotted and try to move around the cost plane and identify what value of theta and theta naught in 3 dimensions yields the lowest cost, because we want the lowest error between the predicted label and the actual label, right? So the goal is the lowest, like the smallest difference between predicted label and actual label. So how is this done? We use something called gradient descent, okay? Now this may look a little scary, but let's take this step by step. So this is what we just discussed. We have some parameter x1 and x2. We can call them theta 0, theta naught, and theta, whatever you want, and then y. Y in our case is our cost function. That is the function that defines loss, or cost. And these are our 2 parameters. With some combination of these parameters, we can identify, hey, these 2 parameter combinations yield the lowest cost, and therefore we input that into the S curve, the sigmoid function, and we get something that's really, really accurate. Okay, how is this done? This graph can be converted into something called a contour plot. Maybe you guys are familiar with contour plots. Like if you ever look at a map, every topographical map has one of these. Like for example, the mountains, they'll have like these squiggly lines over them. And so this contour plot, it's based on the idea that we're drawing lines at points that have the same heights. All right? So at any point on this circle, it's the same height. So that's why it says 8.000 here, 10.000 here. These, any point on this line with x1 and x2 will have the same height. And so let's say we put some arbitrary point on this graph. Now, let's remember that the goal is to get to the bottom of that three-dimensional graph, to get to the lowest cost point based on our parameters, x2 and x1, or theta naught and theta. And so let's say that our x1, x2, theta naught, theta combination starts at this point. And really, where are we trying to get? Like, where are we trying to get in the graph? Yeah, the middle, right? Right here. This is the lowest point in cost. So now, what we can do is, we can take the gradient. And the gradient, this is the tangent line. So this is the tangent line. And the tangent line will tell us where can we go to stay within the same altitude. The gradient will tell us where to go to maximize altitude. Okay? So this tangent line tells us, okay, if you follow this line, you'll stay within the same area. This gradient says, if you go this way, you'll go to the highest possible altitude. We don't want to go to the highest altitude, we want to go to the lowest altitude. So we just take the negative gradient, which is just the opposite arrow, which looks something like this. I'm sorry for the jaggedness. But yeah, so we are trying to, instead of maximize height, minimize height. And that's just the opposite of gradients. And a gradient is kind of delves into more of calculus, partial derivatives with respect to x1 and x2. And you'll see more of that within the code. But the key idea here is that we're taking this tangent line and using it to generate gradients that tell us what is the best way to get to this point. Right, this lowest cost point. But we're not doing this once, we're doing this iteratively. The idea is that we use this negative gradient and we get to this point. We get to this new point here in the 8.000 range. And then we move our weight value. Okay, so then we say here, okay, here's our weight, here's our tangent line, here's our negative gradient. And we keep going and take these small steps until we get to this lowest value. Or lowest value. Okay? So that is the key idea of gradient descent. And how does the cost function play into this? The cost function, which looks like this, is y. It's what defines what our three-dimensional curve looks like. And so we're plugging in x2 and x1 into this cost function, and we're using that and identifying all these different points on the graph and kind of graphing this three-dimensional plane and trying to ski down this slope, basically. That analogy is used quite often. So now that we're done explaining that concept, I'm open to questions if you guys have any questions. Oh, someone said that it was hard to see what was on the whiteboard. Sorry about that. I'll make sure to show it better next time when I'm drawing on the whiteboard. Any questions from here? Okay. Wow, you guys are understanding this way faster than it took me to review all this information, so good on you. So now the point of gradient descent is to update our theta parameters. And so we're updating these theta parameters. I'm consistently reminding you, what's the point? What's the point? What's the point? We're updating these parameters so that we can input that into the S-curve, or the sigmoid function, and create a classifier that will accurately predict labels based on X inputs. And so this is what gradient descent looks like. So we initialize our starting point on the graph. So we say time equals 0, and we repeat, and it's a little bit more complicated than this, but this is what it basically looks like. Time equals time plus 1, so we're increasing one time step. Then we're updating theta. So we're saying theta at time step t equals theta at time step t minus 1 minus the step size, or it's really referred to as the learning rate in the industry. We'll call it the step size, multiplied by the gradient. And the gradient is a partial derivative. And you'll see that we don't actually refer to it as a gradient in the code. It will just be the derivative of the cost function. Okay, and that's what the gradient is, the derivative of cost function with respect to two different variables. And then we're doing this, we're iterating through all of this until we reach our valley. Now the stopping criteria can be different, because if we look back at this graph, let's say you get to this point. This graph, like the way it's formulated, it's not a graph that like you're going to get stuck anywhere. There are no like small valleys, but there are graphs that will have small valleys where our parameters will be tricked and say, okay, this is the local minimum, so it must be the global minimum, and then it gets stuck and that's it. And then we don't reach our lowest cost. So there are methods that we can use to reach that lowest cost by, for example, having a number of epochs, like number of iterations, and once the number of iterations ends, then the code ends, and whatever parameters we have, and that's it. So stopping criteria varies, and if you do more research into logistic regression and in higher dimensionality, there are different ways to say, okay, we're done with gradient descent. Let's output our parameters. Let's see what our accuracy looks like. And so at this point, we have fully reviewed logistic regression. So if you guys have any more questions, let me know. And if no, we will get right into the code implementation. I'm really excited for this. So it's really key that you understand these conceptual, all these conceptual ideas, so we don't get stuck later in the code. What's going on?
So I have a question about gradient descent in the cost function. If the cost function outputs the y, which becomes like what the values that we use for gradient descent, why couldn't we just run through the cost function? Or is that literally just what the gradient descent is mapping?
That graph is just a visual representation of what gradient descent sees when it starts. It says, okay, we see based on initialized value of x1 and x2, this is what the cost is. I'm going to iterate through the cost function, try different x1 and x2 values, and try basically the best combination of x1 and x2 till we get to the lowest cost. And the way we find the best values of x1 and x2 is kind of moving along down the graph with the gradient technique that I showed you. Basically looking at a point, looking at the tangent line, seeing the way to get to the maximum altitude, and then negating that to go to the lowest altitude. So gradient descent is iteratively looking at that graph basically and saying, how can I move best to reach the lowest cost? And moving is adjusting x1 and x2. Does that make sense? Does that answer your question?
That makes more sense.
Okay, great. We have a question in the chat. So the cost function represents how accurate our model is, and gradient descent lets us get the best model. Yes, Addy, that is correct. That is correct. So now, let's get into the code. Yeah, we're just looking for a global minimum. Yep, that's right. So, drink hot water here. Open your favorite IDE where you'll be able to install libraries. That's really important. We're not going to be using any crazy libraries today, but it's important that you have your IDE open so you can follow along. So now, let's get into the code implementation. Let me exit this. bear with me guys, it will take me a few seconds to get this ready. Okay, let's open our IDE. PyCharm. Okay. Okay, let's make that a little bit more clear. Okay. People on the live stream, can you tell me how that looks for you guys? I'd like to know if you can see that clearly. Just because I don't want you guys to see blurry code. So it's important to me that you guys see that fully. Okay, let's go to, while we're waiting for that answer, let's go to our IDE and start writing our code. I'll just go like this. Okay, there we go. Should be in. Okay. So the whole goal right now is to implement logistic regression as we saw in the presentation. And so the first thing we have to do is import some libraries. So the first library we're going to import is pandas. We also need to import Seaborn, matplotlib, and to measure accuracy and generate our data sets, we're going to need sklearn, all right, and let me bring my chair over here. And you're going to need to install these libraries. So the way you do that is just pip install. And you can install each of those libraries. And the red should go away quite quickly. So let me take a minute to install those libraries. And if you're running into any issues, please let me know. Make sure just to install the name of the library, not as. As is like how we're going to call the library. So kind of ignore that. Just install here. For example, we're going to pip install matplotlib. And then pip install sklearn. Once you guys got that down, everyone in person, just let me know. If you have any issues, please. And everyone in the chat, let me know if you are having any trouble installing any of the libraries. Okay. So, are you guys good with the libraries, or are you still working on it? Good? You're good? Okay, take your time. You're good? Great. So now we're going to generate our data. This is super important. The reason why we're not using a pre-trained data set is because I kind of want to really define what our data looks like. I want to define the amount of samples in our data, the features, redundancies, clusters, and I want to be able to generate this random data and also reproduce it. So we're going to be using the make classification library. So we'll define x and y, and we'll set that equal to make classification. And our inputs are going to be n samples. We'll set that to 5,000. All right. We're going to say number of features. Now, number of features defines, like, remember how we said that temperature corresponds to whether we're going to say yes or no to whether we wore a coat? That's the number of features. Like, temperature is a feature. So we just want one feature because this is a two-dimensional problem. We don't want to do anything higher dimensional because we haven't really learned too much about how to deal with higher dimensions. I haven't really mentioned that too much. It involves a little bit more math. So we'll say redundancies equals 0. These are all inputs that I'm not going to go into too much, but it allows us to customize the data we're working with. And that's really cool about sklearn. Sklearn has a million different functions. The one you should 100% avoid, the ones you should avoid are the functions that they make for algorithms. They're great functions, but I just think implementing algorithms from scratch is super powerful and really, really fun. So try to avoid using those sklearn functions as much as possible because implementing from scratch allows you to learn a lot about the math, and also it's just fun. So let's move on to creating all the functions. We're going to need a bunch of functions in Python to allow us to execute our code. And the first one is going to be our hypothesis function. And we'll call that sigmoid because that's the name of the curve. It's a sigmoid function. And we'll say return 1 over 1 plus np.exp. All right, numpy provides this little method called exp, which allows us to use e, and then our input will be negative. Okay, and remember that's how we defined it previously in our PowerPoint presentation. So that's a sigmoid function. So yeah, and we can print out values, or we can graph this function if we'd like. It's really up to us. So now with the sigmoid function, we need to define the cost function. So let's go back to our little presentation here. And we remember that the cost function is defined as negative y log h sub theta of x minus 1 minus log h sub theta of x. All right. And you can see here that if y equals 1, this term is canceled out. And if y equals 0, then this term is canceled out, obviously, because when we plug in those values, we see that these terms are canceled out. And that's how it should work, because this is how we're defining our cost function. If y equals 1, then negative log h sub theta of x. And if y equals 0, then negative log 1 minus h sub theta of x. Okay, so here's how we define our cost function. And we'll call this function cost, or we'll say cost function. And we have a few inputs. We have x, y, and theta. And so the first thing we need to do is take the length of our y output data. And we're going to be using this to average our cost, because cost is averaged over all the data points. We're not taking the cost of one data point, we're taking the cost of every data point corresponding to the predicted output versus the actual output and averaging it. So first we need this value m, and that will be the length of y. And then h is our prediction, and our prediction is sigmoid x at theta. Why the at? All right. In Python, when you're multiplying matrices, you want to use the at symbol, because if you use the multiplication symbol, you'll run into numerical errors. It's really important that you use that at symbol when multiplying matrices, and you'll see that used in the cost function a little bit later. So that is what that at symbol means. And if you don't have too much experience with matrix multiplication, I wouldn't worry about it. But that's what it basically means. And then we need one more variable, and we'll call it epsilon. And this is kind of the same type of formulation. In the cost function, if our predicted probability is either 0 or 1 exactly, then the log will divide by 0. And so we need some epsilon value that will allow the input to be really, really close to 0, but not exactly 0, so that our log doesn't go crazy and we get infinite outputs or a divide by 0 error. So this is kind of manual error handling we have here. And then so now let's define our cost. So our cost is equal to 1 divided by m, and that's just the average, all right? So 1 divided by the length of y multiplied by, here we go, negative y transposed matrix multiplied by the log of h plus epsilon, and don't worry, I know this might be confusing right now, minus 1 minus y transposed matrix multiplied by the log of 1 minus h plus epsilon. Okay, and then we're going to return the cost. Okay, very confusing. What does this all mean? So what does this mean, this cost function? So what we described previously is that 1 over m is the average. And this transpose, what does transpose mean within matrices? Transpose means you're switching the rows and the columns. And so we're taking the negative y value, switching the rows and the columns, matrix multiplying that by the log of h plus epsilon minus 1 minus y, transposed matrix multiplied by n plus np dot log 1 minus h plus epsilon. Why are these matrix multiplication symbols here? Why are these transposed? Why does dot t exist here? So this dot t accounts for multidimensionality, dimensionality above 2, okay? And so if you look at a one-dimensional array, all right? Let me move the MacBook this time to make sure that the people at home see it. Oops. Okay. Here we go. Let me make myself a lot larger so you guys can see the whiteboard. Okay. If we have some array, and we'll call it A, of n, okay? And this is one-dimensional. So we have A of 1, A of 2, A of 3, all the way to A of n. A sub n, not A dot n. If we switch the rows and the columns, what is this going to do? It's just going to become A of n equals this. That's not really doing anything. Like, we haven't done anything to the array. But if we have something that looks like this, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then switching, sorry for my bad handwriting, then switching the columns and the rows drastically changes things. But since we're working with one feature data, which means our input is going to look like this, we don't have to worry about transposing our matrices. But later on, in fact, we will have to worry about this if we have higher dimensionality problems. So for example, if we were trying to predict whether I was wearing a coat based on the temperature, based on some quantified way of saying what my mood was, based on what I saw in the weather app. Like, if we were adding more and more and more features, then we would have to use this technique. But because we have one feature, and even in our code, we define n features equal to 1, we don't have to worry about this transpose. But when I initially coded this, I took into account scenarios that had more than one feature. So that's why transpose exists. All right, so let me make myself significantly smaller. Move the MacBook back here. Hopefully you guys at home saw the whiteboard. Okay. So any questions on that? No questions on that. Let's check the chat. Great. Okay. So now back to the code. So we've created a cost function. Now it's time for gradient descent. Remember, gradient descent is taking our cost function and iterating through a bunch of different values, different x1 and x2 values, or theta naught and theta values, and identifying the lowest cost. Okay? So gradient descent works like this. We'll create a function gradient descent, and we need the following inputs. We need input x, y, our parameters, we'll call them params, or we'll call them parameters. We'll have our learning rate. This is our step size. I said how, this is referred to different ways. And our number of iterations or epochs. Okay? Now, m is defined as len of y, and we can create this as a global variable, but I'll just do this for now. Now we need to create some basically array of values, or array, like some data structure that will store all of our cost values, so we can plot over time how our cost decreases, hopefully, if we do this right. So the way we do that is we create some variable called cost values, and we equate that to np.zeros, and that is for every iteration, epochs, my bad. For every iteration, we're gonna calculate a cost. So right now we're just initializing an array of length epochs, and we're saying let's have this array be filled with zeros, just so we can add values to it and not worry about creating a new array or any of that. So now that we have this cost values, we can start gradient descent. So we say for I in range epochs, because our stopping mechanism in this case is the amount of epochs, and we can play around with that if we'd like. We'll say params equals, or parameters, equals parameters minus the learning rate divided by m multiplied by x transpose matrix multiplication sigmoid of x matrix multiplication of parameters, and this subtracted by y. Okay. Let me explain this. So if we go back to our presentation, remember that the way we update, let me just share this. Let me see here, let me add another window. Okay. Remember that the way we update theta, or our parameters, is we say theta minus the step size, or the learning rate, multiplied by the gradient. The gradient is the derivative of our cost function with respect to our parameters. So, if we go back to our code, and let me take this out. If we go back to our code, that's what we've done in gradient descent. We've said parameters equals parameters minus the learning rate. And then the partial derivative, the gradient, is 1 over m times x transpose matrix multiplied by sigmoid of x matrix multiplied parameters minus y. This here is the partial derivative with respect to our parameters. And we're literally multiplying this by the learning rate. And maybe to make this easier for you guys to understand, what we could do is we could define gradient equal to that and then just do learning rate multiplied by our gradient. And that makes things a lot more simple, right? Now we can see that our gradient, or derivative with respect to our parameters, is 1 over m multiplied by x transpose matrix multiplied by sigmoid of x matrix multiplied by our parameters. Why are we doing this? We're inputting our sigmoid function based on what we think our sigmoid function should look like, calculating the cost, and then updating our parameters. Like, just take a moment to process that, because every time I look at this problem, it's so crazy how we can use mathematical tools that we see in our day-to-day that we don't see as useful, like derivatives, that useful. They're useful for acceleration, velocity, but this is a whole nother level. Like, we can use partial derivatives to identify the way a parameter can be adjusted to fit a classification problem. It's mind-blowing. So that is gradient descent. We are iterating for Ayn Rand epochs, and we are creating some gradient, and that gradient is allowing us to essentially move downwards, or move towards the lowest cost, move in the right direction. And we multiply that by our step size, or our learning rate. Okay? And that is gradient descent. And so we update our cost by saying cost values at iteration I, or at epoch I, equals the cost function of x, y, and our parameters. And then, finally, we return some tuple with our cost values and our parameters. So that is truly gradient descent, and we've implemented the cost function here. So our algorithm is done. We have successfully implemented logistic regression. At this point, all is left is to just have some predict function. And our predict function takes our optimal parameters and feeds them into our sigmoid function. And then we will compare the optimal parameters in the sigmoid function output versus our actual output and see what the accuracy is. And we just look at the discrepancy between the two. And that's how we really measure accuracy. So again, at this point, does anyone have any questions? Does anyone in the chat have any questions? I'll wait a few seconds. Okay. So now our predict function, as I described, we'll create some predict function with our x input and our parameters. Okay, and we'll return np.round because it's essentially our sigmoid function is outputting a probability, which means it's not going to be 0 or 1, so we need to round our output. And so we'll have our sigmoid and x matrix multiplied by our parameters. And so that is our hypothesis function in action using the parameters we updated through the use of gradient descent and the cost function. All right. So at this point, we have two main tasks left. What we want to do is implement all the functions that we just made. And then what we want to do is measure the accuracy. So we need to do some data cleaning to make sure that when we're multiplying our matrices, everything works well. So bear with me here. I'm going to set y equal to np.new axis. And we're just adding dimensionality to our y that we're not going to really use. It's just used for matrix multiplication. And we need to kind of do the same thing for x. And np.hstack allows us to also modify the dimensionality of our x array. And we're just going to add a bunch of ones right next to all of our x values because we need extra dimensionality in our data for the matrix multiplication to work. And so I have to set m equal to the length of y. I forgot to do that. And the last thing we have to do is we're going to define our iterations and our learning rate. So we'll say epochs equals, we'll set it to 1500, and our learning rate, the learning rate is the step size you take from adjusting the x1 and x2 parameters each time through gradient descent. And we want it to be, like, usually it'll be smaller like this, but because we can update this later for better accuracy, we can play around with these numbers. I'm just going to put 0.1 and 1500 epochs for now, and epochs is a synonym of iterations. And then we're going to have to initialize our parameters to a bunch of zeros, two-dimensional zeros. All right. And so the way we do this is we have some variable and we'll set it to np.size x and 1, and this is all just so we can create lists that we can multiply together for our algorithm to work. And so once we've done that, we can now begin computing things. So initial cost, we can compute that by saying cost function x, y, and our parameters. And we can print this out. Hopefully we don't have any errors. If we do have errors, I'll tend to those. Let's print our initial cost. Oops. Oh, I spelled zeros wrong. That's funny. There we go. Stop and rerun. Okay, so this is our initial cost. This value, 0.69312,718. Please, it's really important that you should be able to print out this value, because if you're running into errors now, I'd like to help you before we get more and more complex. Let's look at the chat. Any questions here? Doesn't seem like it. Okay. So we've printed out our initial cost, and we can format this and say initial cost with parameters. All right. And you can, oh, what's up, Tal?
Does scikit not work with Python 10?
Scikit-learn Python 10, 3.10. I'm not sure. If you're running into any errors with that, it's possible for you to install an earlier version of scikit-learn that might work with Python 10.
I can also probably just downgrade that Python version.
That's also an option, for sure. All right, and you can do this. You can format it. All right, so we can print that out. So hopefully that will be able to print out. Okay, initial cost with parameters 0.693122718. All right, we want to see this cost value drastically drop as we adjust the parameters. So now we want to execute gradient descent. So we'll set cost vals and optimal parameters, this tuple equal to gradient descent. And our inputs will be x, y, parameters, our learning rate, and epochs. Oops, spelled epochs wrong. There we go. Okay, now what we can do is we can print our optimal parameters by just doing the same thing we did previously. We can actually copy this and say optimal parameters, and this will be a list because remember our parameters are two numbers, that slope, that w, and that b bias. Okay, and parameters, we'll say optimal parameters. Oops, okay, and let's print that out as well after gradient descent. Has no, oh, I did dot instead of a comma here. There we go, should fix the error. Okay, optimal parameters are these two values. Okay. So these are the parameters that our computer or our model identified as the best parameters that lower cost. How can we validate that cost has actually been lowered? How do we validate that our cost actually worked? So the way we do this is we create a plot with matplotlib. All right, so we'll do this way. We'll create a figure. And what we'll do is we'll plot our cost values as y, and as our x, the length of our cost values, because this is the amount of, basically this is the epochs. This is the amount of epochs. We can also just write epochs in here. So we can just write this epochs, whatever you'd like. And something useful to know is how to label the x and y axes of your graph. So the x label will be iterations or number of epochs, number of epochs, we'll call it that. And the y label will be the cost values, cost value. And we can show the plot like this, and if you want to add a title, you may. All right. And finally, we'll be able to see what our cost values are and how they decrease. So if we run this, there we go. That is our graph across 1,500 iterations. Tal, did you get it working?
I'm actually downloading Calendar right now.
Okay. Don't worry, I'll be able to tend to you in a bit. So we have our cost values here. We have the number of epochs, number of episodes, iterations, whatever you'd like to call it. And you see that we started at this value, 0.6931278, whatever. And that's where it starts. And as gradient descent is implemented over time, we hit this minimum loss, and then we're not doing anything. So really, if we wanted to cut it off at 400 iterations, we could, or even 600 iterations, it's possible. Now, we've seen that cost was minimized, but I want, again, to validate that our model actually worked and that our model is accurate. And here we'll use something useful from sklearn. So sklearn.metrics, import accuracy score. And so our Y predictions is going to be, we're going to use our predict function and X and our optimal parameters. And the way we measure accuracy with this function is we just use their accuracy score method, input our predicted labels, their values, or the data's values, and we print our accuracy score. And we see that our accuracy score is 91.64%. Now, for a model that you trained on your own, that's not pre-trained, that you wrote, I would say 91.64% is pretty good. If we play around with the number of iterations, if we play around with the learning rate, this can increase or decrease drastically. So let's see what happens if we make the learning rate a lot lower. Let's add 2 zeros to the learning rate. Let's see what happens. So why does the accuracy not change that much if we decrease the learning rate and added 2 zeros to the learning rate? Do you guys have any ideas? Do you have any ideas why? Like, I just added 2 zeros to this learning rate. I took it from 0.1 and divided it by 100, and now it's 0.001. Why is the accuracy so close? If you remember the previous graph, you might be able to give me an answer. So this graph, it looks like this, and now the graph looks like this. Why is the accuracy kind of the same? Do you have any idea?
The decrease in the learning rate means you're getting to the bottom of that graph, like the global minimum slower, so it takes more iterations.
So an increase in that means the step size is larger, which means what?
So if the step size is larger, then
You're getting to the bottom?
you're getting to the minimum faster.
Right. And if the step size is smaller?
Then it takes more iterations. So,
But why is the accuracy the same then? It was 91.62 and now it's 91.42. You're getting to the same point. And remember that you see how this is getting smaller and smaller and smaller here? Do you know? Like in the previous graph, we got smaller at 200 iterations because the step size was a lot larger. Now that the step size is a lot smaller, we use almost all of our iterations trying to find the global minima. And the idea here is that if you have a cost plane, if you have a three-dimensional cost plane that's really complicated, you're going to need a smaller learning rate. But if your cost plane is straightforward and it's just like funneling down like what we saw, you can use basically any learning rate because it's going to be pretty easy for the algorithm to find the global minimum.
So in the first graph, the minimum cost is around 0.2, but in the new graph, it's like 0.5-ish.
Yeah, because it has not reached the minimum cost yet. So if we increase the iterations, we'll double the iterations to 3,000. Yeah, so now it still hasn't reached the minimum cost. So even when you double the epochs, it's still not there. So let's put it at 10,000 even and see if it reaches the minimum cost. Yeah, okay, now it kind of reaches that cost that we were at previously. Thanks so much for coming, yeah? Have a good day. So yeah, that's basically logistic regression, implemented completely from scratch. Thank you guys so much in person, on YouTube for tuning in. Let's see if anyone has any final questions. So yeah, I really enjoyed making this, and I really enjoy learning about machine learning and kind of teaching it. So thank you guys both online and in person for giving me the opportunity to teach you. If you have any final questions about resources to learn machine learning, how I learned this, or any just general questions, I'd love to answer those over chat or in person. I'm free here to help you guys out. Tal, were you able to figure that out?
Yeah, I didn't realize actually that it wasn't going to work with 3.10. I probably would have done better ahead, but I got Conda downloaded. It should work. The only thing I have to do is skit or skit.learn, and then I should be good.
WK Games, I appreciate it. Have a good day. I really appreciate you joining the stream. Thank you so much. Thanks for coming, man. I really appreciate it. What's your name? I didn't catch your name.
Walker.
Walker?
Yeah.
Are you, what year are you?
I'm a third year.
Oh, nice. That's awesome. What are you studying?
Electrical engineering.
Hell yeah, dude. Nice. Like, what are you interested in most? What are you interested in most, like, in relation to electrical engineering?
I'm still not sure. Probably the circuits for the signals.
Nice. How have you found your major so far?
It's pretty fun.
Yeah?
It's different.
I think I've seen a picture of you, like, at the Fulton Center.
Oh, really?
Yeah, like, there's a picture of you doing something at the Fulton Center, I'm pretty sure, but, yeah, like, have you kind of done, like, internships relating to electrical engineering yet? It's hard to find, right? It's really hard to find opportunities like that.
Yeah.
Yeah, dude, I'm so into Arduino and stuff like that. Like applying like machine learning stuff, like with Arduino, like computer vision. I think that stuff is so crazy. Have you been able to? You've been able to work with Arduino probably.
A little bit.
Raspberry Pi.
Not much Raspberry Pi.
Okay. And like, what type of tools do you use to build personal projects?
Personal projects? Like for electrical engineering? Or?
Yeah.
Yes, I mean, we use a lot of Verilog, which is like it's a hardware description language. It's similar to other programming languages. We use Cadence, which is like a circuit simulation tool.
Cool.
As well as LT Spice is simpler version of it.
Nice. I appreciate you coming because I've seen you at like every like one of these, but I haven't had the chance to talk to you. So thanks for coming. I really appreciate the support.
Thanks for doing this.
Yeah, absolutely. Have a good one.
So I've all the code written, but I'm still trying to get all the dependencies running.
All right, let me just. All right, everyone on the live, thank you so much for coming. I appreciate you for staying tuned. Make sure to subscribe to the channel. We're at like 992 subscribers, so let's try to get to 1,000. And